Welcome back. I'm in the middle of studying functions and particular classes of functions that show up throughout mathematics and logical reasoning. These include surjective and injective, and today we'll study bijective. We have two separate videos on injective and surjective. You may wish to watch them before. I want to focus today on the computational, diagrammatic, and logical implications of this family of functions. What I have behind me is the Unicode coding of symbols, characters. It replaced the older version, ASCII, which addressed only the English language characters. Now we have many more characters, including mathematical symbols and emoji. The encoding here is to assign a specific number to a design of a letter or symbol or character. Here the Unicode number 0041 is assigned to A, and the mathematical symbol of a circle times is assigned the number 2297. These are in hexadecimal notation, so there's allowed to have letters up through A, B, C, D, and E. So 263A is the smiley face. Each of these characters has been decided by an international convention, and there's a character for each allowed number. So what kind of a function do we have when we study Unicode, ASCII, or other kinds of alphabets? We can look at this through the lens of the equations that are satisfied by such a function. The property we've just articulated for Unicode is a property shared about many functions. It starts with a data type A and transforms it to a data type B by substituting the symbols in some appropriate program. Remember that a function from A to B is one that, when given data of type A, is guaranteed to return data of type B. What it might do on other inputs is up to the program design. Perhaps it won't be allowed, or perhaps it'll throw an error. What we're interested in is what happens when we give a reliable value as a possible outcome. If we have B of type big B, and we ask for f of x equal to b, we have, in a sense, an equation of the letter x. It may or may not have solutions. In our previous videos, we already articulated two of the ways that we could study the equation f of x equals b. We saw that surjective functions were exactly the functions where f of x equals b has at least one solution. Injective functions are when f of x equals b has at most one solution. So today it makes sense to introduce the combination of both. That's known as a bijection. F of x equals b has exactly one solution. We now see the logic behind the naming strategy. Ejective is for an arrow. Injections go straight in without losing any of the information. Surjections are onto, meaning that they cover all possibilities. And a bijection is that both injective and surjective are satisfied. Looking at it this way, we have a head start on some equivalent ways to describe bijective functions. For example, we saw that surjective functions were the same as having a right inverse, and injective functions were the same as having a left inverse. So it's sensible that a bijection has both a left and a right inverse. Being a bijection, we have both a left and a right inverse, which we previously denoted as f slash and slash f. But in fact, it's even stronger than that. It turns out that f slash and slash f are exactly the same function. This claim is stronger than it may seem. Recall that when we had surjective functions, we were guaranteed to have a right inverse. For example, one of our surjective functions was to assign work orders to clients. There was no one who was a client who hadn't ordered something from our company. However, many clients could have solved several orders. So to have a right inverse, we simply had to know how to look up one of the orders. For example, we could say, look up the client's most recent order. But we could have also looked up their oldest order or their most expensive order. Those are all one of the many choices for finding a right inverse of the client lookup. The left inverses of injective functions were also non-unique. But once we get to bijective, we're asking for a balancing point of something that has a left and a right inverse, and there it turns out to have exactly one solution for any inverse, left or right. In this particular case, f itself knows about its inverse. There's no ambiguity as to which one we want. We give that a special notation. We write f to the minus 1 to mean the unique inverse. This one can't be confused as being on the left or the right because there's only one to choose from. Once more, this is just suggestive notation. It behaves like an inverse, but it is not actually taking 1 over f. This algebraic property of inverse functions is often what we need when we compute. We'll have equations that have an f somewhere in the way, and we want to get rid of it. If we have the inverse, we apply it to the left or the right to get rid of it. Keep in mind, we could also have done that with injective and surjective, but only on one side. We should also ask for something diagrammatic and set theoretic to describe these bijections. We start with the function f from a to b. Then, from that, we have that it has an inverse. If we put the inverse after f, then we get the identity on a. We also have the inverse on the right. So whenever our function leads to these two pictures, we can then say diagrammatically that it has a bijection. It is an invertible function. One of the wonderful reasons to translate into diagrams is that we see them in flowcharts. But there's even more going on. As we start to develop more and more constrained situations, we may need to pull back on which functions we can actually use for one context to the next. Remember that we sometimes want to create functions within some context. We'll narrow that context and only allow functions that are preserving some of the properties we want. We would then want all of these diagrams to take place within that special context. If they do, then they become the inverses that we need. One last thing. If we think of A and B as having set properties, we can start to describe things like size. Size is an important component in programs and computation because it lets us predict how many resources are there and whether we've seen enough data to study the problem correctly. For example, we know that the number of Unicode values matches precisely the number of characters, and that's not a fluke. This is a bijective question. Every single character is assigned a unique number, and back and forth. Because of that, we can say that the size of A and the size of B is exactly the same. Once there's a bijection between sets A and B, then the cardinalities, the sizes of the two sets, are created equal. Conversely, most set theories in mathematics and science are designed so that the reverse is true too. If the size of A equals the size of B, it's a promise that there is a bijection from A to B. It may not be computationally feasible to construct a bijection from A to B, but knowing that the size of two sets being equal is the same as bijection is an effective way to predict models in our computations. It may seem at this point that I've picked three very nice families of functions out of the sky to study as I wish. But it turns out every function is actually composed of putting injective, surjective, and bijections together. Even more generally than that, if we need to study just a family of functions and not all functions at once, we can often get by with these diagrammatic versions as alternatives to the descriptions of injective, surjective, and bijective. Many categories have the property that we can still take apart their functions into those three building blocks. You can see the appeal. If we're given functions that are surjective, injective, or bijective, we're giving ourselves the promise that there is at least one way to go backwards on whatever we've done. This is often what a computational problem really is. We're given some process that has produced some output data, and we want to recover some input that did it. And an inverse function would do that. Whether it's on the left, right, or on both sides, simply clarifies what techniques we will need to come up with. We can't guarantee that all of those are computational or easy to find, but it gives us a target to shoot for. But it's even stronger than that. We can even narrow our study to functions that come from special classes, categories, and decide whether there are injective, surjective, and bijective alternatives just from the diagrammatic picture. When there are, then our programs can actually be used within that specific category without modifying the data in illegal ways. And that's often a property that we need to exploit when studying our problems in realistic data structures. In our next videos on functions, we'll concentrate on how to create injective, surjective, and bijective functions from functions that we're given. It may not always be feasible computationally, but at least it gives us a chart to aim towards. Until next time. That's how you take care of your chalkboard.